we're going to go over moments, because moments are really important to me, because moments are on my bike. Now we're back here, I have a lever here, that's really important. We have all the levers here at the back on the brake pedals, and we also have a couple of moments here that we call a couple. Is when you pedal, it's just two forces times the distance between them. Now, another reason moments are important is because when you're on my bike and I want to hop and balance, I have to make sure that the sum of the clockwise moments always equals the sum of the anti-clockwise moments. And then this enables me to balance. Now I can balance just hopping around. Or I can balance when I was moving along, and we call this doing a manual. And doing a manual looks something like this. So as you can see, as I'm riding along, the sum of the clockwise moments equals the sum of the anti-clockwise moments. Otherwise, I would flip off the back of the bike, I'd look really wussy, and I'd do a short manual, and my front wheel would be on the floor before I knew it. Right, so we need to know two things about moments, and it's important not to get them confused, because we can sometimes in the exam. Right, the first thing we need to know is the definition of a moment. Now, the definition of a moment comes from this equation here. Now, F times D, force times distance. Well, what does that actually mean? Now, that D there is a special D. It's actually displacement. And really what we're saying here is this is a force times a perpendicular distance from a point. So if we'll do that in a diagram, we'd have a point here like that, and then we have a perpendicular distance. And just to reinforce, perpendicular, all perpendicular means it's at right angles. So at right angles, perpendicular. That's what it means. So what we're saying here is this force here is acting at a perpendicular distance from a point. And it's pretty obvious that the moment will be larger the distance gets, or the larger the force gets. That's pretty straightforward. Now, let's have a look at that in action. Now this is my telescope here, my first telescope, my first proper telescope. It's a Russian TAL-1 telescope. It's really, really heavy. But the principle of moment still applies here. Now, this is a motor drive. We also need to make sure the motor drive is under too much stress. So, we balance out the telescope. We make sure the telescope has equal and opposite moments. So, if we look at this here, the telescope, we have the large body of the telescope here must be, it's got a large mass, so it must create a large weight force. And then we've got this other weight force here on this end here. So force is high, force is low. But look at the distance. It pivots around this point here. It's just a short distance, and this is a long distance from this. That tells me that the moments on this side must equal the moments on this side, otherwise the telescope would flop to one side or the other. And that makes sure there's not too much stress on the motor. It's easy for us to move the telescope around. So as you can see here, this is the definition for the equilibrium of moments. Now, for an object to be in equilibrium, the sum of the anti-clockwise moments must equal the sum of the clockwise moments. Right, the next most important thing about moments, after the equation and the definitions, is the centre of mass. Now, the centre of mass is so important. Now, for the AQAA syllabus, you're just going to have to know the centre of mass for regular objects that just have a rectangular shape or a cuboid shape, and you must know, well, basically it's pretty straightforward. All it is, if you've got any object that is a regular shape like this, you just draw two straight lines through it, and the centre of mass will be exactly at its centre. The thing you will have to know is you have to think about what's going to happen in different situations, so if the centre of the mass increased or decreased, and whether the turning forces would need to be larger or less. So I always like to, at this point in my life, think about goats. I like goats. Goats are cool. Now, I can't make a goat noise. I can do a sheep noise. I can do other noises. I can't make a goat noise. I'm sorry. But I can pretend to be a mountain goat. Now, the difference between regular goats and mountain goats is that mountain goats have shorter legs. Now, that means they're less likely to fall over. So, for example, if I was a mountain goat and I was, let's say, over here. Now, Being a mountain goat, I'm not going to have long legs. So I know if I walk across here like this, and my legs are long, I'm going to find it harder to balance. So the mountain goat has shorter legs. I'm going to walk along like this. It's closer to the ground, its centre of the mass is closer. So this tells us that the mountain goat will be more stable. It'll have a more stable equilibrium. Centre of mass is really important for moments, it's really important for goats, so we need to appreciate it. Right, let's have a look at some examples where we're going to have to use moments and centre of mass. Right, a classic example of moments is to do with rulers. Now, it's important we understand what's going on here. Now, the ruler has, we're assuming that the ruler, if this is a uniform object, if the wood's pretty good, the centre of mass is going to be exactly at 50. Now, we can test that out just by using it on here. Just trying to balance this at exactly 50 centimetres. So as you can see there, we've got the ruler now to balance approximately, and it's roughly at 50 centimetres. If I just go away by 1 centimetre, 0.001 metres, the moment is still caused from the centre of mass of this object here. It must be the centre of mass. So all I've got is 0.01 times the weight force of the ruler. So I'm going to put this weight force on at the 80 centimetre mark, right at the centre of mass. Now, what I've got to try and do is balance out this ruler. So, if I can balance this out, I know that the clockwise moment and the anti-clockwise moment are equal. So from knowing 3 things, what I can do is I can calculate the weight force of this ruler. We need to know that moments is force times perpendicular distance, and those 2 units need to be in newtons and in metres. So, we have this mass here. Now, I'm going to put that down to 3 significant figures because the mass actually says 100. I'm not sure whether it's 1, 2 or 3, but I'm going to assume it's 3. Now, we're going to have to times that mass by 9.81 to change it into a weight force. So have a go now, convert it into metres, convert that to newtons, and then have a go and work out the moment on that side. You should have found you've got your calculator 0.16677. Right, okay, I'm not going to do anything with that yet. I'm not going to put units on, or round it up, or anything like that, because we haven't finished. Our aim was to find out what the weight force of the ruler was. Right, next is one of my key important things. This is what I love about moments. I work with this, and if you get into this every single time, you'll be able to work out and solve any problem on moments. You've just got to identify whether forces are acting and remember centre of mass. Right, I'm going to keep that number there. I need that. For any object in equilibrium, we know that force 1 times perpendicular distance from a point 1 must equal force 2 times perpendicular distance from the point of 2. Now, it's completely irrelevant which one, F1 and F2, you decide, you make sure. Now, just the principles here, what I'm going to say, I'm going to call this F1, and I'm going to call that distance there to there, D1. This obviously is going to be F2. This here is going to be D2. Right, now, if I have any number of forces on this side, I can just extend that and just say F2 times D2, add F3 times D3, add F4 times D4. Now, we're just focusing on this first of all. Now, we know that all of this here must equal 0.16677. Right, so let's write this out. 0.16677 must equal force 2 times distance 2. Now we have distance 2, okay, from the measurement there. 13 centimetres, 0.13 metres. So 0.16677 equals F2 times 0.13. We need to rearrange these equations. So, if I've got times on this side, we need to do the inverse law, so we divide that by 0.13, which means we have to divide this side by 0.13. Okay, they cancel out. Right, have a go now and work out what the weight force of the rule is. Why are we doing this? Stop. Come on, let's stop. I've got a ruler, I've got a mass. I'm just balancing on a telescope and a clamp stand. Okay, this isn't interesting. But actually, wait a minute, it is. This is so important. Now, this is the first basic building blocks of engineering. Now, if you are going to be an engineer, you have to know about moments. It's crucial. I told you about my bike. Okay, all those moments, all those properties are based on moments. Now, you can't build anything without knowing about moments. So, to understand things at this basic level, with just a ruler and a simple weight, then you can apply it to any sort of new situation. And in fact, I've seen exam questions on bikes, on levers, on vertical lift-off aeroplanes, and loads of different situations. So this can be applied to absolutely anything. So it's crucial we understand a ruler and a mass. If we can't do this, then it's going to be pretty hard to understand what's going on in a vertical takeoff aeroplane.